Well, that's interesting. We've now learned a little bit about the roots, the real roots if they exist. There'll be 1 positive, 2 or 0 negative ones. Well, if you turn to the back of your important concepts, or you probably printed it out as 2 pages, the rational zeros theorem. The rational zeros theorem tells us that if we have rational real roots, and rational numbers are numbers that can be expressed as fractions. A number like the square root of 3 is not a rational number. That's what we call an irrational number. 5 is a rational number because it can be expressed as the fraction 5 over 1. 1/3 is a rational number. It's indeed being expressed as a fraction. So this would be an irrational number. These are rational numbers. And the rational numbers theorem, rational zeros theorem, tells us that if we have any rational zeros, we have any rational real zeros, they will have to come from the fractions that we can form by taking the factors of the constant and putting them, looking at the wrong one, the factors of the constant and putting it over the factors of the coefficient of the highest power term, which in this case happens to be 1. So what we do is we form what we could maybe call our P's and Q's. P is all of the factors of the constant. Q, those are all the factors of the coefficient of the highest power term. So if we think of the factors of 8, that'd be plus or minus 1 times plus or minus 8, right? Those are 2 factors of 8. Plus or minus 2 times plus or minus 4. So our P values here come from that set of values. The Q values would come from the factors of 1. Well, the only factors of 1 are plus or minus 1. And then the possible rational real roots have to come from the fractions that I can form by putting every possible P value over every possible Q value. Well, in this case, the Q value is only 1. So I'm going to be putting those numbers over 1, which is just going to be those numbers again, isn't it? 1 over 1 is 1, 8 over 1 is 8, 2 over 1 is 2, 4 over 1 is 4. So in this case, the P over Q rational numbers end up being the same as the P values, which doesn't always happen. If the coefficient had been 2, that would change things for us. And we'll look at an example like that in another video. So if, there's no guarantee, but the rational zeros theorem tells us that if we have any rational zeros, they have to come from this set of numbers. They have to come from that set of numbers. And Descartes told us that there'll either be 2 or no negatives, and there'll be 1 positive. So out of these numbers, one of those positive numbers and perhaps 2 of those negative numbers would be the real zeros if we have rational real zeros. Now, we may not have rational real zeros, but these techniques we're looking at are aimed at finding the rational real zeros that might be there. So if we have any rational real zeros, they have to come from this set of numbers. Well, let's just kind of take one and see what happens. Let's pick one of the numbers from this set of numbers and test it to see if it's a real zero. Now, I'm going to show you a technique for testing whether or not a number is a real zero. It's a technique called synthetic division. If the number is a real zero, we can perform this synthetic division, and the remainder we get should be 0. In effect, when you perform synthetic division, you are taking this polynomial. Let's say we're going to let's try a negative number, since we're potential is we have more negatives here than positives. Let's try the negative 1 as our first trial for finding a real 0. So in effect, what we are doing is we're taking this polynomial and we're going to try to divide it by x plus 1. And that's what you're really doing when you test with this synthetic division. You're taking that original polynomial, f of x, and you're trying to divide it by x plus 1 when you're testing negative 1 as to whether or not negative 1 is a real 0.